Okay, ji. Bismillah ar-Rahman ar-Rahim. And the previous lecture, we were discussing the basics of packet switching network and what a basic packet is, and we were understanding why it's important for packets to be created in the first place. What added benefit does a packet switching network offer as opposed to your conventional circuit switching network that was used before in our telephonic conversations? Now, we looked at what the overall packet structure looks like, what the header, the contents of the header are, the role of IP addresses, the sender and receiver's IP addresses, the how packets are basically traveling on different paths to their destination, and when they arrive at different times, that means they are tend to be out of order. Now, how are we ensuring that they are brought back into order? What is the importance of a sequence number, so on and so forth? And we saw that a packet size is usually about 64 KB bytes. And after that, we also understood that your trailer, for example, has details on how and when your packet is ended, so that if information is being received by some terminals or a computer, and that computer will be able to identify that this is the end of this packet structure, and any data that is following this packet structure is not to be linked with this current packet. This basically allows for packets not to get mixed up. There could be millions and millions of packets arriving at your computer right now. And this trailer information is basically helping in segregating packet information from each other. And following, as mentioned before, data transfer techniques is one issue, and making sure that the data transfer has been carried out correctly is a bigger issue. So we have to make sure that once information has been transmitted from source to destination, it actually arrives in the correct order as expected. So we'd have some sort of error checking mechanism. The error checking mechanism we saw in the previous lecture is not actually that, in depth. It's not that perfect, but it's somehow, it's working, it's doing something, it's trying to avoid any sort of corrupted packet being transferred. Okay, now let's move on to understanding the basic role of packet switching, and then we'll be looking at an example of how a packet is divided and what happens when it's reaching its destination. Okay, now packet switching. Let us now consider what happens when a photograph. We are still continuing with the exact same example that we were discussing in the previous lecture, that we are transferring a photograph over the internet. So basically, if it's a large image and we're dividing into smaller parts of that image. So if it's a, say, 34, 35 MB image, now we have divided into KB byte chunks, 64 KB byte chunks, right? So let's now consider what happens when a photograph, for example, is sent from computer A to computer B. The photograph will be split into several packets before it is sent. Essence of packet switching is that we will divide the data into small size chunks. Each chunk is known as a packet. There will be several possible routes for the packets between computer A, which is the sender, and computer B, which is the receiver. So as you can see here, my computer A first accesses the router that is nearest to computer A. We'll call that router A. Now, and this router, which is immediately closest to my destination computer, computer B, it will be called as router B. Now, between router A and router B, there are lots of routers. So you can say, I mean, we only have 10 represented here, but there can be many more. And your internet, the whole infrastructure, the network of networks is basically a very elaborate mesh of interconnected routers, many routers. Now, these routers allow us to communicate easily with the whole internet. Now, this is the beauty of the internet as it is. We are communicating with this huge network that is basically covering the entire planet, and we are treating it as just one network. It's just one internet. It's just a single entity. And we never say that I will look this data up I'm looking for some document on the internet. I didn't find it on internet A. Let's look it for it on internet B or C or D. No, for us, we're just searching the internet and we will find it there. And for us, there is only one internet. And this huge network operates as a single entity for us. And it's just, everything is just a click away for us. It's just a hyperlink away from us. So the way that it's operated like this huge network is operated collectively as a single entity is through these routers. So my request is basically route is passed through these routers to eventually the destination. And it doesn't matter where the destination is. My routers will eventually make it reach the destination. So the server that I'm trying to contact maybe is in North America, and you will access it through these routers if it's allowed. If the access is allowed, then you will be able to access that information through these wide range of routers that are all connected to each other at some point. So basically, we have this huge number of routers here. Now, you note that routers 1 to 10 represent the routers, and these routers can also be called the nodes, as the nodes were in our circuit switching network. These work in a similar way, and they are between the routers of network A and network B. Okay, so packet will be split up to, the photograph will be split into several packets before it is sent. There will be several possible routes for the packets between computer A, which is sender, and computer B, which is the receiver. Each stage in the route contains a router. As you can see, these are all routers. The router receives a data packet and based on the information in the header, decides where to send it next. Now, as you can see here, it states here, based on the information in the header. As you remember, the header contained some very vital pieces of information, such as the IP addresses of the sender and the intended recipient. Now, basically, I'm using that information, or not me, but the routers, the interconnecting routers in between, are basically using that information to determine where the packet has to be forwarded. Now, let's just imagine I'm sending an image from my computer. That image is divided into several chunks, and those packets are forwarded from this router to this whole network over here. Now, each packet has its own header, and the header contains information, which is the addressing information, which is the IP addresses of the sender and the receiver. So in this case, if when a packet reaches, say for example, it reaches this router over here, this router will analyze the IP addresses mentioned in the header of that packet. And from there onwards, it will determine which router should it forward it to. Now, as I think I've mentioned this before, but these routers, they seem like a small thing, but actually they are full-fledged computers on their own. They are capable of making complex calculations. And these computers or these routers are capable of deciding which is the best possible path from this position to the intended destination of the packet. So if this router has received a packet, this router will analyze the destination IP address and see which path should be the best path to reach from here to here. So for example, if it determines that the best path is say from router 5 onwards, then it will forward it to 5. And if it determines that router 1 onwards is the better path, then it will forward to router 1. If it sees that its better path is to router 6, then it will forward to router 6. And when it, for example, reaches router 5, the router 5 will take the exact same set of steps. It will see, okay, now I have received this packet. The destination states that I have to reach this place. Now from here, which is the best possible path? Maybe I will choose this, maybe I will choose this. So whatever is the best possible path, this router will forward that packet to that router. And this router does the same thing. Every router that's receiving packets will do the same thing. And eventually that packet will reach its destination using the best possible path. Now, there is this data structure that each router maintains, which is known as the routing table. And that routing table is basically the sort of the key information that each router relies on with respect to what router to forward it to. So that router table, it gives you this key, gives each router the information that this, for example, router 2 looks at the router table. It will see that, okay, router 1 is available, 5 is available, 6 is available, and they're all in the path of reaching my destination. So which one should I choose? Well, distance matters here. So if, for example, something is closer, I would, or the distance overall from the sender, the original to the, sorry, this router to router B, the distance, whichever path is the shortest, this router might choose that path. And there are other factors as well. For example, it sees that router 1, 5, and 6 are all three of them available, but only it seems like router 6 or router 5. So for example, router 5, I have option router 1 and router 6 and router 5 as well. I can forward this packet from any one of to any one of these routers. But it seems that router 5 is the least busiest. Router 1 and 6 are very busy. They're processing other routers and they seem like they're unavailable. And if I forward it to, even though it seems like router 1 provides the shortest path, but since router 1 is very busy, I am better off sending the packet through router 5. And thereby, I may have a great chance that by this path, the packet will reach this destination faster. Now, one interesting aspect here is that imagine that you're, for example, traveling on a road, right? And you have different paths. You have different paths. You have different routes to take from your source to your destination. For example, you're going from your home to your school. Now you're arguing with your friends that we should take this route to our school. It's much faster. The distance is shorter, and it will get there in by covering lesser distance. Now it's lesser distance, no doubt, but the roads are crowded. That's one aspect. Another friend says that no, we should take the longer route. We should take a ring road, a high-speed highway, and that way, the way is faster, the way is longer, no doubt, but we will get to school sooner. So there's two arguments here. One friend says that we will take the inner city route, and it's a little crowded, yes, but we will, consume less fuel because we're moving shorter distance. And on the other hand, the other friend says that no, if we take the highway route, yes, we'll burn more fuel, we're traveling more distance, but since the crowd is less, there's less traffic signals, we will eventually reach the school sooner. Now, these are two arguments. Now, you can choose between these two paths based on what is important to you. Is saving fuel important to you, or is saving time important to you? If, for example, saving fuel is important to you, in that case, you will obviously go for the inner city route. However, if time is important to you, then you will go for the highway because you want to get there faster. Now, you choose these two routes based on the requirement, your requirement at that time. Okay, now when it comes to our network communication, the only factor that is considered when choosing different paths is time. Only factor. Nothing is more important than time. I just want to relay information faster. I just want to make sure that each and every packet reaches its destination in the shortest amount of time. Nothing is more important than time here. So if, for example, the longer path means that I will get to my destination faster, I will take it. And maybe the shorter path, if it wasn't busy, which it is right now, if it's busy, then it will cause me to wait a lot. So that it's better to take the longer path and I will reach my destination. So nothing is more important than time in terms of network communication. There is no other deciding factor, it's just the time. So whatever path you take, it may not be the shortest path, but your router will definitely choose from all of its options and select the path that takes the least amount of time. So that's the one leading deciding factors with respect to choosing paths between adjacent routers, which router to go to next, so on and so forth. So when we say that router is a computer, yes, nothing can be more accurate. Yes, it is a computer. It is actually doing calculations, constantly doing calculations. And that router table I just mentioned, that too is a changing data structure. Say, for example, this router 5 has to determine which packet to forward, which router to forward to, router 3 or router 8. The data structure is showing options like these two. Let's just say router 3 has become disabled for some reason, some technical fault or whatever. So router 5 will adjust its data structure to reflect this information now, and every other router will have updated information as well. That no longer router 3 is available. Now whatever path you take, router 3 will not be part of it. And if they, for example, don't have updated information and to their records, router 3 is still available, they will forward the data and they send it to router 3, which is not capable of processing any sort of packets right now. And that will result in packet loss. That packet is lost because it reached a dead end. So this is how a router is working very intelligently and making sure that your data is received at its destination in its entirety, first thing. Second thing, in the shortest amount of time. Okay, now let's consider this example over here. Each packet can be sent independently from start to endpoints. That is the, again, essence of packet switching network. At the destination, the packets will need to be reassembled into their correct order. So obviously, we will be using the information in the header. Again, which header information is this? This is the sequence number. At each stage in the transmission, there are nodes that contain a router like this. Each router determines which route the packet needs to take in order to reach its destination. The destination IP address is used in this part of the process. So again, I'm consulting the header information. In this case, that's the IP address. Now again, this example contains the packets. So imagine that this photo that I'm trying to transfer is divided into these 5 packets. Just for example, is divided into 5 packets. Now, as the essence of my packet switching network goes, each packet will go through a different path and arrive at the destination collectively, but not collectively, but they will eventually reach the destination. But since they're taking different paths, it definitely means my packets will arrive out of order. That's exactly what's happening. So let's say that my packets, red, blue, green, purple, and maroon, are traveling along this between these mesh of routers, reaching this destination. So my sending computer divides the data into packets, is forwarding it to the adjacent router, and that router forwards it to over the network. Now you can see here, the green packet is traveling from this path to this destination. The red packet takes its own path, its own route, and travels and reaches the destination like so. The maroon path takes its own, the maroon packet takes its own path, which is the destination. Same thing goes with blue and purple. They all take their own destination, so on and so forth. Each packet is taking its own destination, and eventually it will be ending up at the router. As you can see here, my data has changed. Now the packets, since they arrive at different times, the sequence has changed. The original sequence was red, blue, green, purple, and maroon. However, I have what here? Red, purple, maroon, green, and blue. So the order of packets has changed. And that was expected because each packet is traveling a different path to its destination. And since it's following a different path, each packet will have different arrival times. And because of those arrival times, the packets have shifted around. And this is where the computer B will be using the packet header, which is the sequence number, to rearrange the data in its correct order. Because that's what's happening in the computer. Each packet will follow its own route. Routers will determine the route of each packet. The routing selection depends on the number of packets waiting to be processed at each node. So if my router T2 has to decide between router 1, 5, and 6, it will decide on which router, it will decide on the router that has the least amount of work to do. That is the freest in a sense. And by freest, we means that it has least amount of route packets to process. If the other ones are busy, then it's no point to sending to them because this packet will have to wait there. So I send it to the packet that I've sent it to the packet to the router that is the has the least burden right now. The shortest path available is always selected. This may not always be the shortest path that can be taken, since certain parts of the route may be too busy or not suitable. Now, in this case, shortest means the path that causes my packet to reach in the least amount of time. So again, it's not necessarily the shortest path ever in the entire network, but it means my router has selected the shortest path at that particular moment with that particular burden of packets of each router. In that particular moment, my router, for example, router 2, saw that all adjacent routers, amongst all connecting routers, router 1 seems like this least busy, forwarded to that. And each, say router 1 does the exact same thing and chooses to send it to, say, packet router 5. Router 5 sends it to router 3 because router 8 seems busy. Router 3 sends it to router 7 because 4 seems busy, and 7 sends it to 9, or sends it to 10 directly because 10 seems the least busy, and that's why. Now, this path that was just taken, router 5, 2 to 5 to 8 to 7 to 10, it might not be the shortest path. There may be shorter options apart from this, but considering the status of each router at the hopping point, the routers that have been chosen at each hopping point have been selected on the basis that they are least amount of busy right now. So if a router is busy, it has a lot of packets to process, it will be avoided because this packet going to that router will eventually cause it to wait. Unfortunately, packets cannot reach the destination. Packets can reach the destination in a different order to that in which they were sent. And that's the additional processing overhead that my computer B will have to endure because it will have to rearrange the package to correct it. If it doesn't do that, then the data that is being just sent to him will be meaningless. So that's one of the drawbacks of packet switching network, that my sending computer will have to divide data into packets, and my receiving computer will have to rearrange data into its original form. So other than that, it is a very secure method. I will know which packets have, even though packets have found their own way, and most of them, there will be minimum packet loss, and almost all of the packets will have reached the destination. And those packets that have gone missing can be requested and resent. But it does ensure the maximum reaching of data. And of course, since I have maintained this sequence, I can rearrange the data to its original form at its destination. So this is basically an example of how packet switching takes place. And currently, this packet switching and this mode of data transfer is dominating our internet data transfer. Most data transfer is being carried out in this way.